Okay, good morning. So we're going to continue discussing today the kind of large-scale history and evolution of the universe. A reminder, if you haven't already, to please sign up for the required tour of the Museum of Paleontology here at Berkeley. There's an email with sign-up times. So if you haven't already done so, please take a look at that. Any questions? Yep.
One of the days said Wednesday on Thursday night. Is that correct?
So,
Wednesday Yeah.
yes. Sorry, yes. So there's also a Wednesday time. Yep. Another question? Yep. No question. Okay. Any other questions? Okay. So in particular, we're going to continue our discussion of what is in the universe and how it came to be, focusing on the role of gravitational runaway in the expanding universe as really the origin of galaxies, which are in turn where planets, stars, and life itself gets going. Then I'll talk a little bit more about the connection between the properties of dark matter and the properties of galaxies. So where is the dark matter in relation to galaxies? And then at the end, I'll address a question that's really a thorny one right now in a lot of people's thinking about the history of the universe itself, which is if some properties of the universe were a little different than we actually think they are, if there was a little different amount of dark matter, if the expansion history of the universe was a little different, we think that actually would fundamentally alter the likelihood of life arising. And I'll kind of talk you through some of the issues. This is really, again, one of these forefront questions that's at the interface between cosmology, the science, and more philosophical aspects of the field. And then at the end, I want to kind of take stock of where we've come in the class and where we're going, because this really does mark a shift. Having completed the majority of our astronomical and geological understanding of origins, we're going to really be turning more to biological, things like climate change, evolution, the likelihood of evolution around other planets. So that's kind of where we're going in this lecture. So I want to start, again, with this picture of the sky as seen with a microwave telescope. So just to remind you, if you look up at the sky with a microwave telescope, it looks like the sky is almost uniformly glowing the same in every direction in radio waves, microwaves. Microwaves are just part of the radio, part of the electromagnetic spectrum. If you look in exquisite detail with really, really good telescopes, that's only been possible in the last 10 or so years, what you see is that actually different parts of the sky have very slightly different amounts of the thermal background radiation or the microwave radiation. And we think this radiation, remember, is really the glow left over from about 400,000 years after the Big Bang. The universe was very hot in its early stages, produced this thermal background radiation. As the universe expanded, at some point, about 380,000 years after the Big Bang, the thermal radiation started traveling freely through the universe without running into electrons and atoms and things like that. And so these tiny differences in the amount of microwave light on the sky encode the state of the universe just 380,000 years after the Big Bang. And so the question I want to start by asking you is, what does it tell us that when we look across the sky, above us, beneath us, to the left, to the right, what we see are these extraordinarily small differences in the amount of microwave light, the amount of thermal background radiation from one part of the sky to another. So here are four possible interpretations of those small differences in the amount of microwave light that we see. One is that initially there were actually very large differences from one place to another, but they've just averaged out as the light travels over billions and billions of years to get to us. Second possible answer is that the near uniformity of the thermal background radiation is an indication that the temperature in the early universe was actually nearly the same everywhere. Third possible answer is that just knowing this microwave light and its uniformity is actually not enough to tell us about the conditions in the early universe. And the last possibility is kind of the opposite of this one, is that the temperature was actually very different from one place to another. So talk to each other about these four options. Think about what information is really encoded in this thermal background radiation. So I see some blues. So go ahead and raise up. So those of you who are putting up, so there's a few greens, mostly blues. So somebody who's putting up a blue, why? Why does this tell us that the temperature was nearly the same everywhere? How do you go from this to that? Yeah.
Well, assuming that since the differences are so small, that would imply that basically the same.
Yeah. So that's the right reasoning. The fact that there are these tiny differences is an indication that in the very different parts of the universe, places that started out way up there or way down there, that their properties had to actually be quite similar in the early universe. And in particular, remember the special thing about thermal blackbody radiation is that the properties of the light are determined by the temperature of the object that's emitting the light. And so in particular, the uniformity in this thermal blackbody, thermal background radiation is an indication of the near uniformity in temperature in different parts of the universe. And so this is really a quite astonishing inference that we can go from the light we see today to the inference that 380,000 years after the Big Bang, the temperature was actually almost the same in what are now parts of the universe separated by billions of light years. In that early phase of the universe, those different regions had almost identical temperatures. And that directly follows from this observation and from the fact that thermal radiation really just depends on the temperature of the gas. So there's a follow-up question I want to ask you now, having established this, which is, given that inference, do you think that life, at least life that we have some vague idea of what it might be like, would have arisen under these conditions in the early universe, when the temperature was relatively similar in different places? And again, I'm going to ask you why. So 2 answers here, yes, no. But also think, so what is the reasoning behind your guess? I see a number of greens going up, an occasional red. So again, talk about this for a second. Okay, so I see a lot of green. So why? Somebody who has a green held up. Give me a kind of justification for no, which is the right answer. Yep.
Well, those conditions, the temperature was above 3,000 degrees.
Yeah.
So there's no way that life can arise.
Yeah, so one answer is, well, the temperature was 3,000 degrees, which is pretty hot. Certainly, life as we know it would have been incinerated under those conditions. Any other reason for no? Yeah. Yeah, so another one is there isn't actually any carbon. It's mostly hydrogen and helium, a little bit of lithium. So we don't have the kind of building blocks in terms of atoms for life. There's another one, which is that life, as we know it, requires actually differences in conditions from one place to another. Think about the story about the origin of life in the hydrothermal vents. It was the large difference in conditions in the gas bubbling up out of the hydrothermal vents and the ambient water, in particular in that case, the large difference in pH and proton content that established differences in energy which allowed chemistry to get going under very uniform conditions where things are almost the same everywhere. It's very hard to get chemical reactions going. So there's actually a lot of reasons for thinking that under these nearly uniform, rather boring, pure hydrogen and helium and dark matter conditions in the early universe, that we don't think that life, again, at least as we know it, would have been able to get going. And so this is an extremely important point, right? What it tells us is that 380,000 years after the Big Bang, the distribution of normal matter throughout the universe was actually extraordinarily simple, much simpler than it is today. It was a nearly uniform gas of hydrogen and helium with almost the same temperature and density from one place in the universe to another place in the universe. There was none of the complexity that we see around us today. No stars, no galaxies, no planets, no life, no complex molecules, nothing exotic as far as we know, like black holes and neutron stars. So it really was this extremely simple, very smooth universe in this early phase. And that really is a direct inference, again, of the observations of the thermal microwave background radiation. And that's one of the reasons that this provides such an important clue to our origins, is the information that it contains not only about the geometry and the makeup of the universe, but really the very state of matter about 380,000 years after the Big Bang. And so the question I want to start addressing today is, how do we go from this very simple beginning to the much more inhomogeneous, complicated, lumpy universe that we see around us today, where an average place in the universe is still actually kind of boring. It doesn't have much matter. The space between galaxies is largely devoid of much stuff. There's a little hydrogen, a little helium, a little dark matter. But there are these rare regions that host galaxies, stars, planets, complex molecules, and life. And so how is it that we transition from this smooth beginning to the inhomogeneous structure that we actually see around us today? And once again, the story of how we go from relatively smooth to relatively clumpy is a story of gravity. It's, again, this critical process of gravitational runaway that not only is the process that forms stars and planets, but it's also the process that takes the very smooth initial state of the universe and converts it into the inhomogeneous universe we see today. And this graph is actually a graph I've already used because the basic idea is the same as gravitational runaway when we talked about the process of star formation. There are very small differences in temperature and density in the early universe. That is kind of captured by those small differences in the amount of thermal light from one part of the universe to another. And those small differences get amplified by gravity as time goes on. And that's illustrated schematically here. This is density of matter as a function of where you are in the universe. There are initially regions that happen to have a little bit more stuff than other regions. Those regions have stronger gravity. And so the stronger gravity of regions that happen to have a little bit more matter pull stuff in. And so as time goes on, the regions that started off with a little bit more stuff end up pulling in more and more matter. And so small differences in density get amplified by gravity as time goes on. And that's the heart of this idea of gravitational runaway. Now, one critical difference between this kind of version of gravitational runaway and the version we talked about when thinking about how stars and planets form is that on the scale of the universe as a whole, most of the matter is not normal matter. It's dark matter. And so gravitational runaway on the scale of the universe as a whole is actually dominated not by the gravity of normal matter, but it's dominated by the gravity of most of the stuff in the universe, which is actually dark matter. And so it's the density of dark matter, it's the gravity of dark matter that dominates this gravitational runaway process. And remember, I talked about last time about how really the key distinction between dark matter and dark energy, the stuff that's causing the expansion of the universe to accelerate, is that dark matter clumps, it's inhomogeneous, it's not moving very fast, so it responds to gravity. By contrast, dark energy is relatively smooth, it's uniformly distributed, and so it doesn't participate in this gravitational runaway process. And so for the universe as a whole, this gravitational runaway process is really dominated by dark matter. Normal matter contributes and participates in the gravitational runaway, but it's not the dominant source of gravity on large scales because there's 7 or 8 times more more dark matter than normal matter. Okay? Any questions about this? Okay. So I want to show you some examples from computer simulations of how we think this gravitational runaway process unfolds. And so this is first a snapshot from a simulation. It's a computer simulation actually only of dark matter. There's no normal matter in this particular simulation. Things start out about 500 million years after the Big Bang, relatively smooth. In this panel from the computer simulation, you don't see much differences from place to place. And as time marches on, the differences in the amount of matter start to get larger and larger. The regions with lots of dark matter are regions that look very bright, very white, high kind of density of stuff corresponds to white in these images, and very dark blue or almost black corresponds to a very low density of dark matter in these images. And so you can see as time goes on, you can see the smooth beginnings getting amplified into a much more inhomogeneous distribution as time is going on. from about 500 million years after the Big Bang up to basically the present day, about 13.7 billion years after the Big Bang. So this is a snapshot. And so what I'm now going to do is actually show you an actual movie of this kind of computer simulation. This particular movie, the scale of this movie is about a few million light years across. And so just to remind you, the size of our galaxy is about a few million light years today. And so this computer simulation shows kind of the history of the formation of a galaxy like our own in dark matter. This computer simulation, again, only has really dark matter. It also has dark energy. It doesn't have any normal matter. And the reason is that there really isn't all that much normal matter in the universe, so you can get a pretty good understanding of how things clump up as time goes on just following the dark matter. Yep?
How would normal matter behave differently?
So the question is, how would normal matter behave differently? And I'll come back to that in just a few minutes. So for now, I'm focusing on the dark matter because that's the dominant force in determining how things clump up. And we'll come back to what the normal matter does in just a second. And so this particular simulation starts about 400 million years after the Big Bang and goes to the present. Time in these computer simulations is denoted by this quantity that's called redshift. And redshift basically is a measure of the average distance between objects. So in the distant past, the redshift was higher, and that means the typical distance between objects in the expanding universe was smaller. So initially, as the computer simulation evolves, you saw material started to move out, but rather quickly, gravity in this part of the universe, which was denser than other parts of the universe, the gravity of this part of the universe was strong enough that it actually stopped the material from expanding out with the expansion of the universe, and it pulled it back in to actually form our galaxy. So let's start again. So you notice initially things expand out. And then as time goes on, that initial expansion out gets halted by the strong gravity of this initial region, which is denser than average. So the fact that this initial region is a little bit denser than its surroundings causes its gravity to win out over the expansion of the universe in this little small million-year patch of the universe. And what ends up forming is this kind of swarm of clumps of dark matter orbiting around. And this is really the picture you should have in your mind of what our galaxy looks like in dark matter. In dark matter, it's this swarm of clumps of dark matter orbiting around under the kind of combined effect of the gravity of all of the dark matter that makes up our galaxy. And the stars and gas in our galaxy, as we'll talk about it in a little bit, are really just in a very small region here at the center of the galaxy. Most of our galaxy is just filled primarily with dark matter and very little stars and gas. The stars and gas are confined to the central region of the galaxy.
So can we actually measure the clumpiness of the dark matter, or is it just the result of the simulation?
So the question is, can we actually measure the clumpiness of dark matter, or is it just a bold theoretical prediction? Any guess as to how we might be able to measure the clumpiness of dark matter? Yep.
If we see that, because we can compare how much certain things move at slower velocities,
Yeah, so the suggestion is that if you could observe like a star or gas near this clump, maybe the mass of one of these clumps is so big, it really dramatically changes the speed of objects moving around in our galaxy. And that turns out to be hard. On average, the motion of objects is really dominated primarily by the average gravity of everything, not by the motions of individual clumps. So the way that we can do it is using gravitational lensing. You can see light being bent a little differently if it happens to pass very close to one of these clumps. And so you can use the lensing of background objects to try to directly measure the clumpiness of matter in kind of dark matter distributed throughout galaxies. It's a hard measurement, but this is something that people are really starting to do in some detail now, really only over the last 5 or 10 years. Okay, another question?
There was an example in section of like the bullet cluster where dark matter is passing through, like it passes by itself.
Yes.
So how does that work with the force of gravity?
So the question is, there was this example in section where in a colliding cluster of galaxies, it seems like the dark matter kind of moves through itself while the gas comes slamming to a halt. And that's a big distinction between how dark matter behaves and how normal matter behaves. So the answer there is that those galaxy clusters are moving so fast that what's going to happen is they're going to pass through each other. The gravity of the dark matter acting on each cluster will slow it down, but it'll pass through, kind of overshoot a little bit, and then start to settle back down. And so you can kind of see that in this movie where you see clumps come in and then fly back out before they start to settle down. And it's a very similar idea in those colliding clusters of galaxies. Okay. So I want to show you another movie of this process. This movie now is on scales of billions of light years. And this movie is different than the previous one in that in this computer simulation, in making the animation, what they have done is they have taken out the expansion of the universe. So you don't actually see the expansion of the universe as a whole. The whole box is expanding with the universe as a whole. And so this highlights, in this movie, what's really highlighted is the motion of matter relative to the expanding universe as a whole. And so what you see is that as time goes on, matter clumps up, it gets pulled into regions that have more stuff. It's again the kind of rich get richer kind of phenomena. The regions with more mass initially get more and more mass as time goes on. And these regions here, because this is now 1 billion light years as across, these regions here correspond to locations where you actually have tens of thousands or hundreds of thousands of galaxies. So these are, in fact, examples of very, very massive clusters of galaxies where you have many, many, many galaxies orbiting around under the mutual gravitational pull of the dark matter. Yep. Question?
So wherever the dark matter seems to not be, does that mean that it's really just empty? Do you know what's there?
So the question is, what about the kind of purpley regions, bluish regions where there isn't much stuff? So those are regions where there isn't much dark matter, and there also aren't many galaxies. And so I'll kind of show you this in the distribution of galaxies in just a second. Another question? Yep.
What balances gravity with dark matter if it doesn't collide?
So, right, good question. So like in this calculation, the question is, what is really balancing dark matter, the gravitational pull of dark matter, if it's not colliding or running into anything? And the answer really is it's just the motion of the objects. Objects have this flow, this initial motion, and that, at the end of the day, what is really balancing gravity is just the random speed that things are flying around with. It's similar in many ways to what balances gravity if you just have a collection of stars orbiting around under their gravity. The stars aren't colliding, but it's the fact that they have motion which stops gravity from pulling everything to the center. Yeah, good question. Yep. So the question is, what initiated the motion of dark matter? That's a great question. And that's one of those questions about the very early universe that we really don't have a great answer to, right? We observe that the universe is expanding. We think that's been happening from very early times, but we don't know what really initiated that expansion. We don't know what gave matter in the universe initially its initial kind of kicks of motion that kind of set everything going. And so that's really one of the big questions about the very early stages of the universe that we don't have a completely satisfactory answer to today. Good question. So this shows you, again, on a scale of billions of light years, this shows you the distribution of dark matter as predicted by a computer simulation in the present day. Again, white regions are lots of dark matter. Very dark regions are very little dark matter. And the regions with lots of dark matter are the regions where gravity is stronger because there's more stuff. And those are the regions that preferentially pull in normal matter. Normal matter responds primarily to the gravity of dark matter on the large scales of the universe as a whole. And so these regions with lots of dark matter pull in the normal matter. And so the gravity of dark matter really does dictate on large scales where normal matter ends up. On average in the universe, there is more normal matter, there are more galaxies and stars and planets in patches of the universe where there is more dark matter. And that's because gravity of dark matter pulls in the normal matter much as it pulls in dark matter itself. And so in a very real sense, the distribution of dark matter is the kind of backbone of the universe that determines where the galaxies and stars and planets are distributed. And so when we look up at the sky, this is now an actual picture of how galaxies are distributed on the sky. So we're here, not at the center of the universe, but at the center of this picture. Okay? This is the view of the universe seen from us. Looking up at the sky, distance is going out, and these different kind of directions correspond to different directions on the sky. And you see that galaxies trace out this filamentary or web-like structure. There are regions with lots of galaxies, shown in kind of red and yellow, and there are regions with very few galaxies, shown in black. And that pattern of how the galaxies are distributed is extremely similar to the pattern of how dark matter is distributed in these computer simulations. And that's because the gravity of the dark matter really dictates where the normal matter goes on very large scales. And so the question was, kind of how does the normal matter behave? And this is really on the largest scales, the normal matter really just does what dark matter tells it to do. It moves where the dark matter is because the gravity of dark matter is so strong. Okay? And so you flip back and forth between these two pictures, And you can really see the similarity in this web-like structure of both dark matter and computer simulations and the real distribution of galaxies that we see on the skies. Okay. So now I want to go into a little more detail about how galaxies kind of build up from the early stages when galaxies first started forming a few 100 million years after the Big Bang to the present day. And we think that this process of gravitational runaway in the expanding universe is one that started with first very small objects forming, and as time went on, smaller objects build up into larger and larger objects. And that's shown in this sequence of 3 snapshots from a computer simulation. Early on, there are very small lumps of dark matter, and as time goes on, things build up into bigger and bigger lumps of dark matter. And so this is this kind of general phenomena of what we've called bottom-up formation, starting from small things, building up to bigger and bigger things. And so this shows that process of bottom-up formation, start small, build up bigger and bigger in dark matter, but we actually think the very same thing happened in stars and galaxies. The first stars and galaxies formed about a few 100 million years after the Big Bang, when the universe was maybe 10 or 20 times smaller on average than it is today. And the first galaxies that formed were actually little tiny galaxies that maybe had masses of only 10,000 or even 1,000 times the mass of our sun. And the first galaxy that formed, the very first galaxy that formed, probably only had a few stars, unlike the trillions of stars that make up our galaxy today. And so by galaxy here, what I really mean is a collection of gas held together by the gravity of dark matter, where that gas starts to collapse under its own weight and turn into stars. That process really started, as shown in this computer simulation, with a single star forming at the center of a very tiny little galaxy. And as time has gone on, galaxies have then evolved from these little tiny miniature dwarf galaxies to bigger and bigger galaxies as time has gone on. Okay? So the galaxies start small, but as time goes on, they build up into bigger and bigger galaxies. And we think that that process of galaxies growing in size happens really in 2 different ways. One is that the gravity of the dark matter that dominates the gravity of a galaxy pulls in surrounding normal matter. And that's shown in a computer simulation here. The dashed line is kind of the extent of the dark matter associated with this particular galaxy. And the red stream is a stream of gas being pulled into the galaxy by the strong gravity of the dark matter that makes up this galaxy. So the gravity of the dark matter pulls in surrounding gas, and that gas, as it gets funneled into the galaxy, eventually turns into stars, causing the galaxy to grow in mass and size. And so this is one way that galaxies get bigger. They start off small, but they kind of gobble up surrounding gas, providing the fuel for them to grow in size. The other way that galaxies grow is literally 2 galaxies may slam into each other, forming a bigger galaxy. And so the fact that our galaxy, in about 4 billion years, will collide with Andromeda, our neighboring galaxy, this is not just some accident. This is actually a key clue as to how objects in the universe get bigger as time goes on. One of the key ways that galaxies grow in size is by galaxies literally colliding together, forming bigger and bigger galaxies. And these are actual pictures taken with the Hubble Space Telescope where you can see galaxies in the process of colliding with other galaxies. You see, this is a picture in starlight where you can see these different lumps representing different galaxies colliding with each other. Yep? Yeah, good question. So what dominates the process of kind of things getting pulled together, be it gas or be it other galaxies as a whole, really is the gravity of dark matter, exactly, because that's the dominant gravity on the scale of the universe as a whole. Yep, good question. So we've actually been able to unravel, by observing galaxies at different times, we've actually been able to unravel the history of how galaxies and stars within galaxies form. And so this is a single plot which really conveys 50 years of astronomical work, which is what is, on average in the universe, at some time since the Big Bang is back here, what is the average rate at which new stars are forming? When the universe was very young, not many stars were forming because things were very smooth. As time has gone on and the universe has got clumpier and clumpier, more and more stars started forming. Most stars actually formed about 3 or 4 or 5 billion years ago, which corresponds to, say, 6 or 7 million years after the Big Bang. So this is the peak of star formation, say 4 billion years after the Big Bang, so maybe actually closer to 8 billion years ago. The sun, right, formed about 5 billion years ago. So the sun, in some sense, formed in kind of the old age of the universe, when most stars had already formed at an earlier time, and the process of stars forming and galaxies growing is kind of slowing down in the present day. And this is very interesting if you think about this in the context of evolution and the likelihood of life existing elsewhere in the universe. If most stars formed 3 or 4 billion years after the Big Bang, 8 or 9 billion years ago, then there's been plenty of time for evolutionary processes to operate in different galaxies around different stars, and thus there's really been plenty of time for processes shaping life to happen in a wide range of different environments in the universe. So just to kind of orient you in this picture, again, this is when the solar system formed. We've seen several times this picture of very distant galaxies, the Hubble Ultra Deep Field. And this picture really represents galaxies in their infancy. Galaxies back here, just about 1 billion or so years after the Big Bang, which really represented the first stage of galaxy formation in the universe. Kind of the first generation of stars and galaxies was forming here. More and more of them formed as time has gone on. And then the process of star formation has slowed down in the present universe. And understanding exactly why the kind of buildup of stars and galaxies has this shape is a very active area of research. And there's a lot of aspects of this that we don't actually understand very well today. But this is just directly from observations. Okay. So to kind of bring together then our picture of the expansion history of the universe as a whole, we can really divide the history of the universe into a variety of different epochs, There's the very, very early phase of inflation when we think the universe expanded at an extraordinarily fast rate. We think this phase in the evolution of the universe produced the small differences in density from one place to another that gravity then acted on to build up galaxies and stars and planets. A small fraction of a second after the Big Bang, protons and neutrons formed out of the primordial soup of matter that existed at early times. A few minutes after the Big Bang, protons and neutrons fused together to form helium, lithium, deuterium. After that point, the temperature was too low, and so fusion shut off until stars started to form. About 380,000 years after the Big Bang, when the universe had cooled to 3,000 degrees, the atoms started to form, electrons became bound to atoms, and at that point, the thermal radiation started to travel freely through the universe, not running into anything. And so what we have now filled in the beginning part of this lecture is these last three phases in the history of the universe. As time went on from these early phases, gravity caused the universe to get lumpier and lumpier and lumpier. About a few 100 million years after the Big Bang, the first galaxies and stars started to form. They were very small galaxies with just a few stars. Galaxies got bigger and bigger. More and more stars started to form. Maybe 4 or 5 billion years after the Big Bang, most stars in the universe had formed. And then about 9 billion years after the Big Bang, kind of our solar system formed, an inconsequential event for the universe as a whole, but it just kind of puts our solar system formation and the beginning of life on Earth into the context of the history of the universe as a whole. Okay. So what I want to do now is talk a little bit more about the connection, really, between galaxies and dark matter. We've talked about dark matter as dominating gravity on very large scales, but I also mentioned last lecture that in the solar system, dark matter is kind of irrelevant. So somehow, on very large scales, the gravity of dark matter is very important. But on small scales of individual stellar systems, dark matter doesn't really matter. And so why is there that basic distinction? So we've talked about the fact that galaxies are surrounded by this very extended distribution of dark matter. Most of the stars and gas that make up galaxies are in the very central region. Most of the dark matter is spread over a much larger range of scales. And so the question I want to ask you is, why is there this fundamental difference between where the normal matter is, the stars and gas are in the center in this small region, while the dark matter is much more spread out? In particular, why is the dark matter so much more spread out than the stars and gas in galaxies? Is it because dark matter can't emit light? Is it because normal matter has less rotation, and so it collapses to smaller scales? Is it because there's similar densities on average of normal matter and dark matter, and because there's more dark matter, it's more spread out over a larger volume? Or is it because the dark matter particles don't collide with each other while the normal matter does? This is a hard question. Okay, I'll be honest. This is one of the tougher questions, I think, so far. But talk to each other about this for a second, about what causes this basic difference between how dark matter is distributed and how gas and stars are distributed, and then we'll walk through it in just a second. So which answers are you being drawn towards? So I see some greens. I think Jean is putting up a white, or maybe he just has paper in his hands. A few reds. So the answer that I kind of want you instinctually to be drawn towards is that there's something different, fundamentally different about the nature of dark matter as a particle and the nature of normal matter. And the answers that embody some difference like that are A and D. There's a sense in which A and D are actually both pretty good answers. The answer, I think, that's closest to the actual explanation as we understand it is actually A. As I said, this is a tough question. I think Jean is the only one who got it right. So why is this? Well, the way I'm going to explain this to you is by explaining to you why it is that normal matter shrinks down to this small spatial scale. Initially, when galaxies are first forming, the normal matter is actually spread out just as much as the dark matter is. It's spread out over very large distances, similar to the extent of the dark matter. What happens then is that the normal matter, because it's hot, is able to radiate away, it's able to cool and lose its thermal energy. When it loses its thermal energy, it loses its pressure support. As it loses its pressure support, it no longer has anything staving off the force of gravity due to dark matter, and that causes the normal matter to collapse to smaller scales. In fact, the normal matter collapses down until rotation becomes important, and so it builds up a disk-like structure when rotation becomes important. So it's fundamentally the fact that normal matter can lose thermal energy, it can cool and radiate away energy and light to get rid of pressure support, to collapse down in a rotating disk-like configuration. That's really what sets the size and the distribution of normal matter in galaxies. Now, the dark matter particle, because it doesn't collide with itself or with normal matter, it actually cannot produce light. It cannot radiate away in light its energy of random motion. And so the dark matter stays as this large, puffy distribution orbiting around at high speeds under the action of its own gravity. And so that's really the fundamental distinction between how normal matter and dark matter behave. Yep?
But if dark matter is exerting gravity as well, why doesn't it pull normal matter with it into its big shape?
So gravity, dark matter does pull the normal matter into this kind of distribution, as you saw in some of the computer simulations. But there's also enough dark matter in the center that gravity kind of pulls the normal matter into the central region. So, good question. Yep?
So normal matter is hot, and so it has this internal matter. Then it cools so that it condenses as well together.
Yes.
But so dark matter, since it doesn't have that thermal energy, why doesn't it just collapse?
So the question is, since dark matter doesn't have thermal energy, why doesn't it collapse? The way to think about it is, if you remember when we talked about what temperature really is just kinetic energy of motion. Atoms move faster when they're hotter. And so the fact that the dark matter particles are all whizzing around very fast really is a kind of temperature. It's a lot of kinetic energy, But dark matter has no way of getting rid of that kinetic energy by radiating energy away, by light, and so that's why it doesn't collapse down. Okay. So then, yep?
Does the dark matter halo still get smaller as time passes? Because gravitational runaway
So the question is, does the dark matter halo get smaller as time goes on? Not really. Because the dark matter halo is growing in mass as time goes on, you're pulling in more and more dark matter, it actually tends to grow in size. So what I want to think about now is, what is the distribution of dark matter on different scales in the universe? On average, there's more dark matter than normal matter in the universe. About 7 times more dark matter than normal matter. And so the gravity of dark matter dominates over normal matter in determining how the universe evolves on very large scales. But within galaxies, because the normal matter has all shrunk to the very center, while the dark matter is spread out a lot more, it turns out that within, say, the sun's orbit around the center of the Milky Way, there's about as much normal matter as dark matter. And so normal matter and dark matter are actually equally important at determining the motion of the sun around the center of the galaxy, roughly. Okay? Within, say, regions where stars are forming, those are regions within galaxies where matter is much denser than in an average place in the galaxy. Gravitational runaway has taken matter spread out throughout the galaxy, and it's caused it to clump even further. The dark matter doesn't really participate in the gravitational runaway process that forms our solar system or other stars. And so when we look on the scale of individual stars or individual solar systems, what we find is that the gravity is really dominated entirely by the normal matter. And that's because, again, the kind of gravitational runaway has concentrated the normal matter tremendously, going from the scale of the galaxy as a whole to the scale of the solar system. That gravitational runaway is mostly due to the normal matter, and so you end up with lots of normal matter in a solar system and not that much dark matter. And so in particular, within, say, our solar system, there's about 1 trillion times more normal matter than dark matter. And so you can see, as you proceed to more and more high-density concentrations of normal matter, from the universe as a whole to galaxies to stars, you proceed to regions where dark matter becomes increasingly less important. In the solar system, dark matter is not very important. In the galaxy, dark matter and normal matter are similarly important. And on the scale of the universe as a whole, dark matter dominates over normal matter.
Does that mean that, even here, there's as much dark matter as there is in anywhere else? It's just not that much.
So the question is there a similar amount of dark matter in our solar system to a random part of the universe? Not quite, because if you remember, I showed this image of the distribution of dark matter, where there are lumps with lots of dark matter. The white regions and the dark regions are not very much dark matter. And galaxies do, on average, form where there is more dark matter than average. And so in our solar system, there is more dark matter than average, but there isn't a huge concentration of dark matter in our solar system relative to our galaxy as a whole. So one point I want to just mention, because this ties in with a lot of kind of very active areas of research today that you probably read about in the newspapers, is if dark matter kind of tells normal matter where galaxies are going to form, because where there's a lot of dark matter, there's strong gravity, and that's where the normal matter goes, then why isn't our understanding of how galaxies form complete? Are there parts of our understanding of how galaxies form that we don't still fully understand? And the answer is yes, and the reason has to do with the fact that when you look at individual galaxies, it's no longer only the kind of gravity of dark matter or the physics of dark matter that dominates how things behave. Other forces, other physics becomes very important. And indeed, one of the really remarkable observational discoveries over the last 10 years or so has been the realization that most of the normal matter that is pulled into galaxies by the gravity of dark matter actually gets blown back out of galaxies. And this is an actual, real image, not an artist's conception, of a nearby galaxy. What you see in the white light is the stars that make up the disk of this galaxy. And what you see in the purple light is matter that's actually being blown out of galaxies, in this case, by the effect of stellar explosions. So supernovae, stellar explosions, when they go off, they heat the material up to such high temperatures that the matter actually goes flying back out of the galaxy itself. And we actually think that most of the matter that was at one point pulled into galaxies by dark matter is subsequently flung back out again by stellar explosions and other processes like that. And so we talked about the cosmic cycle of heavy elements that the sun and the solar system is part of. The idea, as Carl Sagan said, that we are all star stuff. And that cosmic cycle actually extends over much larger distances than we originally thought in Sagan's day. What we now know is that the gravity of dark matter brings normal matter into galaxies. Normal matter collects in regions that form stars like our sun. Our sun fuses heavy elements to form. Those heavy elements get dispersed back out into the surroundings, the sun's neighborhood, by stellar explosions and stellar winds. And those processes actually drive most of the heavy elements formed by fusion out into the distant reaches of our galaxy, well outside where the stars and gas are. And so this cosmic cycle of matter and elements that we are part of really extends over enormously large distances. Okay. So what I want to do now is just very briefly mention to you something that people are struggling a lot with right now, kind of at the interface between physics and philosophy. And it's really a set of questions that gets at the heart of thinking about our origins. So I gave you this kind of incredible story backed up by many, many observational results of how it is we think that the conditions for life really got going in the universe as we know it. From the early phases when hydrogen and helium were formed to the late phases when heavy elements were formed. And what people started to realize 10 or 15 years ago is that if the properties of the universe were a little bit different than what we actually measure them to be, that the likelihood of each of these steps happening, and each of these steps seems to be necessary for life to get going, the likelihood of each of these steps getting going would actually change a lot if some properties of the universe were a little different than what we actually think they are. And so I just want to give you a few examples of that. So one example has to do with the expansion of the universe as a whole. If the universe had a lot more dark matter or normal matter than it actually does, say it had 10 or 100 times more dark matter than the universe actually seems to have, in that case, the universe would have expanded and collapsed back on itself due to the strength of gravity halting the expansion of the universe. And this expansion and collapse would have happened before any stars could form. So this universe, a universe with significantly more matter than we actually seem to have, would be a universe where no stars would form. Similarly, if there was a lot more dark energy than there actually seems to be, then the acceleration in the expansion of the universe would have started so early, would have been so rapid, that there wouldn't have been time for gravity to cause things to clump up. Matter just would have expanded apart from itself so quickly, again, that we think very few stars and galaxies would have been able to form. Yep?
By much more matter, that's both normal and dark matter?
Yeah, actually both normal and dark matter. Yes. Okay. So these are just interesting facts about the universe, right? If things were a little different, a little bit more matter, a little bit more dark energy, then it would have been harder for life, at least the history of life as we understand it, to have actually gotten going. Yep?
If there was more dark energy or if there was more normal matter with the expanded matter?
So if there was more dark matter, things would have collapsed back really quickly. If there was more dark energy, then things would have expanded so fast, accelerated so fast, that this gravitational runaway process really couldn't have gotten going. And there are other interesting, weird little puzzles like this. There's a beautiful book by Martin Rees, who's the Astronomer Royal. If you're in Britain, they have kind of neat positions like the Astronomer to the Queen, the Royal Astronomer that we don't get to have in the U.S. So he's the Royal Astronomer of Great Britain. And he has this book called Just Six Numbers, where he lays out that if certain fundamental constants of nature were a little different than they actually seem to be. So for instance, if the charge of the electron was a little different than what it actually seems to be, then it actually would have been hard for carbon to form by fusion in stars. The fact that carbon fuses from helium, carbon is formed by helium fusion, is not kind of generic, but would actually be different if the properties of the universe were a little bit different than they actually are. And so this raises a really interesting question, which is why is it that the amount of dark matter and dark energy, the exact fundamental constants of nature, etc., why do they happen to have values that seem to allow for the evolution and formation of life? And there's really two schools of thought to this question these days. One is, I have no idea, but give us some time. You know, these are hard problems. We'll think about it. We'll eventually figure it out. The other is that maybe we should take this idea that there are different regions of the universe, each of which is undergoing its own expansion. This idea of multiple universes or a multiverse, maybe we should take that really seriously, and maybe in these different patches of the universe, there are actually different fundamental constants, different amounts of dark matter and dark energy. And what that would mean is that in some regions, like, say, this one, there wouldn't actually be any galaxies, any stars, any life, because the conditions wouldn't be right. But our patch of the universe just happens to be one in which the conditions were right for evolution to proceed. And the reason that physicists worry about this, the reason we actually take this question quite seriously, is this kind of gets at the heart of whether we actually have a first principles scientific understanding of why things came to be, or whether we have to kind of rely on luck or fine-tuning or some divine being, right, in order to set the early conditions in the universe and allow evolution and life to proceed. And so it's kind of the connection between this set of issues and what really counts as a scientific explanation. We don't like scientific explanations to rely on having conditions that are very, very fine-tuned, that have to be exactly a certain way. We like our scientific explanations to be a little bit more robust than that. And Charles alluded to this when talking about the origin of life on Earth. And it's actually a very similar set of almost philosophical issues is what drives people to think very seriously about this set of questions that I've raised here. Any questions about that? Okay. So what I want to do in the last few minutes is just kind of remind you where we've come so far in the class and kind of give you a prelude of where we're going to be going. Because in a real sense, we have finished the core astronomical origins part of our thinking about origins. We have an understanding of the Big Bang, the expansion of the universe, the origin of the elements, the formation of planets, stars, fusion, etc. And what we want to think about now is start thinking in more detail about the evolution of life on Earth and the likelihood that similar biological, geological, and evolutionary processes could operate on other planets. And so I hope you have a better appreciation now for this kind of Copernican idea that our solar system and our planet are really nothing special. We are one of many planets and many solar systems that's part of many galaxies, many clusters of galaxies. And really, the kind of where we find ourselves, even the fact that we seem to be kind of naively at the center of the universe is really just kind of a peculiarity of how we interpret the observations. When we look a little more deeply, we find out that there's really nothing particularly special about our place in the universe. We have built up an understanding of the remarkable power of gravitational runaway in forming most of the astronomical objects that we see in the universe. Galaxies and stars and planets. Gravitational runaway plays in some form or another the really central role in thinking about the evolution of the universe as a whole from the Big Bang through to the formation of planets like the Earth. On the largest scales, the evolution of the universe is dominated by dark matter and dark energy. Our material that we are familiar with from everyday experience here on Earth makes up only a small amount of the stuff that actually comprises the universe as a whole. Normal matter is very important for the behavior of stars and planets, but it becomes increasingly less important as you look on larger and larger scales in the universe. Those large scales are really dominated by dark matter and dark energy. we have begun to understand how stars and planets function, and how their functioning is really central to the possibility of life. Stars are hot enough in their center that nuclear fusion produces energy, and it's that energy that is fundamentally what drives life as we know it on Earth and probably on many other planetary systems. And it is that fusion in the centers of stars, that builds up the heavy elements needed for life to get going, for complex molecules to form. We've also seen the remarkable explanatory power of plate tectonics, and we will continue to see over the coming weeks the critical role that plate tectonics plays in making the Earth hospitable, in making the Earth a place that geological and in particular biological processes can operate over hundreds of millions of years. I think one of the really great triumphs of our understanding of origins is understanding how the periodic table of elements is built up from light elements in the Big Bang to the heavy elements formed by fusion in stars and stellar explosions. As I highlighted today, we understand now the sense in which we are literally a form of nuclear waste, right? We are formed from the nuclear debris left over when stars fuse heavier elements, when stars explode, and in that process fuse heavy elements. And it's out of that nuclear waste, that debris from star formation, that life itself got going. We've begun to see how evolutionary processes can cause, due to the kind of overabundance, overproliferation of life, the huge explosion in population that life gives rise to, and the resulting competition for resources that produces, we've seen how evolution through natural selection can produce descent with modification, changes in the nature of populations and species with time in response to changing environmental conditions, genetic mutations giving rise to some examples, some particular species, some particular examples of species being somewhat more fit for their environment than others. And what we will see over the next few lectures is how that evolutionary process took very early life, single-celled, and then eventually multicellular, and turned it into the diversity of animals we see in the oceans, the diversity of animals we see on land, and ultimately through to the dinosaurs, mammals, and primates and humans. One of the themes over the next few weeks is going to be what really determines the habitability of Earth in the sense of the kind of climate or climatic conditions on the Earth. We actually have remarkable geologic information about changes in temperature over millions and thousands of years in the distant past. So we know the geologic record of the history of the climate of the Earth. Sometimes it has been more hospitable to life, sometimes it has been less hospitable to life, and we're going to unravel those changes in hospitability. I think that's a word. And in particular, we'll talk about the changes that have been going on over just the last few centuries, where humankind is now impacting dramatically the climatic conditions that it finds itself in. We'll also see, I think quite surprisingly, that the climate and the likelihood of life evolving, the conditions under which life evolves on Earth, is actually quite sensitive to a variety of astronomical factors. Collisions with asteroids, whether we pass through spiral arms of our galaxy, and exactly what the tilt is of the Earth on its axis, which gives rise to the seasons, and changes in that tilt are actually one of the major causes of long-term climate change and the ice ages and things like that. And lastly, what we will try to do in the last week or so of the course is bring together all of our understanding of astronomical, geological, biological processes to at least begin to talk sensibly about the likelihood of life, either primitive life or complicated technologically advanced life, of existing elsewhere in the universe. I don't know the answer to this question, but we hope that by the end of the class, we'll be able to better discuss and have a better feel for the factors that really determine under what conditions life elsewhere in the universe is likely to evolve. Okay, so that's where we're going to be going in the next few weeks. Thanks.